Hi, everyone. This is Jonathan Palmieri. I'm with Rex Recruiting. I work in the human capital management and technology spaces, consulting companies on how to leverage technology throughout their talent process and engaging employees in a better way. We've all worked with some pretty terrible technology, and HR is definitely no stranger to that. Um, Getting into this project, I came across a need where I wanted to compare two strings together, quickly realizing that it was going to be a little bit more complex because of the variation of the strings. I started exploring how I could use a language model to essentially compare these two strings in a semantic way. And looking at it, I struggled to find a way to do it in Java. So after exploring a couple different ways to do that, I inevitably ended up figuring out a way to use an Onnx model, which is essentially a model that's able to work throughout different language model frameworks. So it's converted almost into a similar language for each one of these frameworks to work with. Again, this is going to be pretty informal. I didn't plan too much into this, but I figured this could be helpful for some people, and I'll try and do a little bit more of a formal write up. So if you see anything that's not correct, let me know. I'm also self taught, so I might not have some of the conventions down that a formal programmer would have. So without further ado, let's jump into it. So for the sake of this, I'm going to use IntelliJ. If at any point you're running into any issues, let me know. Mine is already configured, so that could be one of the reasons you do that. I'm going to do it in a Maven project just to make things easier with the dependencies. I'm going to name this just Playground 2. I'm going to start that up. So here we have just a standard project here. I'm going to create a new class, and I'm going to call it string or sentence comparer. And then I'm just going to write a main class here. And this is going to be the basis of what we do. So step one is going to be that we have to convert, and I'm going to show you kind of my steps through here with my rough write-up. So step one is going to be that we're going to try and convert the strings into a tokenized and encoded way with a pre-trained transformer model. That's coming from Hugging Face's library. It's the all MPNet base V2 sentence transformer. So that's what we're going to use to essentially convert our text into an embedding or mathematical vector form of our words, which we can then use to look at the different predictions. We can use it for word similarities and semantics. For the sense of what we're doing, we're going to do word similarities. So essentially, it's going to encode those. We're going to compare the encodings through cosine similarities, and then we're going to use that number to essentially create a percentage of how similar those words are based on the semantic similarities of the context. So step one, like I said, is going to be creating the Hugging Face tokenizer. So we'll do then I'm going to grab the context from here. So all right there, plop that in there. So because it's a Maven project, we're going to want to add our Maven Hugging Face. You'll see that it's a dependency now. AI DJL Hugging Face. Add it in here. We're going to import that class that's in there. And we're going to import the encoder and encoding as well. And I'm just going to dump all these imports in here just to make it easier. Okay, So we have our Hugging Face tokenizer here. It's duplicate for whatever reason. I'm gonna fix that. There we go. So now we have our tokenizer together. We're going to then now put together our encoding. So we're gonna do encoding. Store that in an array. Encodings equals the tokenizer. And batch code. And we're gonna add our sentences in here. So our sentences are going to be a string of sentences, an array of sentences. Excuse my typing. I'm gonna just put 2 in here. So we're gonna compare the 2 strings. The dog is happy. Dog is sad. All right, so now we have those together. Let me just space this out just to make it a little bit easier. Hopefully everything's viewable on this once it gets up onto YouTube. Now we're going to put together the Onnx runtime environment. That's Microsoft's product that's going to help us utilize the Onnx model. I'll show us how to export that model in a second. So we're going to do ORT environment. We're going to call that environment. We're going to initialize that. I'm going to grab that. That's going to get our environment information for Onnx runtime. We're doing it through Maven, so we don't have to install the runtime directly onto the system. Though that is one way to do it. That's not how I'm going to do it, just for the sense of making it easy and hopefully working on everybody's systems. Then we're going to create the Onnx runtime session. That's going to equal the environment. Sorry, I'm looking over at my notes. Create session. Oops, create session. We're going to add our model in there. See, it's saying model path. And then we're going to do new ORT session with session options. And then I'm going to add the exception here so that if we do run into an issue there, it is caught. And we're going to add in where we put our model. So I'm going to take a break from this for a second, space that in. There we go. To get the Onnx model, we're going to use PowerShell. To do that is explained pretty well in this document, which I can link in here. But essentially, we're going to convert the sentence transformer model, this model right here, this Pytorch sentence similarity model, into an Onnx model. And again, this explains it pretty well, but this is the code that works for me. So we're going to use this optimum CLI export Onnx model. And we're going to call out the model that we want to use and then the location of where we're going to put it. Once you do that, I already did that, so I'm not going to do it again because it takes a little time. But once you do that, you're going to essentially populate your folder with these files right here, which is your converted Onnx model right here, and then some of the other specification information here from the model. You can see those in the model card here, where you can see like tokenizers, config, tokenizer, right? That's just bringing over all that information in a form that we can now utilize. So the next thing that we have to do is we have to give our Onnx tensors. So in order to do that, we're going to create a variable to store those in. So it's going to be long input IDs 0 equals new long, and then we're going to put our encoding length in there. So that's going to make sure that it's the right size to fit. Oops, I did not mean to do that. To fit our input IDs, and then we're going to do our intention mask. from my understanding, the attention mask isn't necessary. Some models you may need to do that for advanced configuration though. The way that I got it working is to use that. So we're going to stick with that. So again, we're going to put the encoding length in there to make sure it's the right size. And now that we have those, we're going to do a for loop, and we're going to do I. So I'm going to specify as an integer for I equals 0. I is less than the encoding length. And then we're going to iterate and add to each one. And now within this loop, we're going to do input IDs 0. And we're going to put our I in there so we can walk through each one of those. And then we're going to go equals encodings. I get IDs. Now this is going to grab our IDs for each one. This is going to do some of that manual work that you may have had to do in other platforms, which is nice. Now we're for the attention mask, we're essentially going to do the same thing. Encodings. I get attention mask. So that's going to assign a lot of the information to describe what the model is going to do, the shape of the model, all that kind of stuff. And now we're going to create our Onnx tensors. So to do that, Onnx tensor input IDs equals Onnx tensor retensor. I'm going to throw our environment in there, and then we're going to put our input IDs. Cool. About that. Now we're going to do another one for our attention mask. So it's going to look very similar. Attention mask equals Onnx tensor dot bring tensor environment, and then we're going to do attention mask. Cool. Now that we have all those together, we're going to create a map of these. So map Onnx tensor. And I'll call that inputs. I'm going to initialize as a new hash map. And we're going to import that. Import it up there. I'm going to just expand this out a little bit so I can scroll up and keep it in view. So where we're at our inputs. So I'm going to add our inputs. So inputs dot put. We're going to call it input underscore IDs. We're going to do sign IDs. Sake of just making this easier, we're going to also add our other side, which is our attention mask. And attention mask. Cool. So now we built where we're storing these. And now we're going to do a try method, try block ORT session. Result, call that results. Session dot run, and I'll do inputs. Cool. Some of this piece. See what the end of that is. So now we're going to do our Onnx value. And that's going to be last hidden state equals results dot get. And do 0. And now we're going to do our float. token embeddings equals note. Go and last get in state get value. Bam lamb. I am missing something there. Oh, that's good. Okay. Now we're going to do another float. Just copy this. Float. So in that one. Sometimes being lazy makes things harder. Sentence one embeddings. That's going to equal our average embeddings to embeddings 0. Don't worry, we're going to create that, so that's why it's showing up in red right now. And then we're going to do our sentence 2 embeddings. It's going to be 1. And I'm going to assign that to double similarity. And that's going to equal the cosine similarity of sentence embedding 1 and sentence 2 embedding. And I'm just going to have that print out so that we can see what that result is. So I'm going to just say similarity. Cool. So now that we have that, we need to now create some things here, the average embedding method and the cosine similarity method. So let's do that. So we have private static float average embeddings. We're going to give that float token lamb. Then that return our average, which we will get to. So we're going to do integer length equals token embeddings dot length. Awesome. Done. And then we're going to do the dimension. So describe shape embeddings dot length. And then we're going to do a float average, which equals the float the dimension. Cool. So then I'm going to do for loop with float embedding. So I'm going to token embeddings. Then another for loop inside of there. Your eye, this may not be the cleanest code, so feel free to clean it up. This is just proof of concept. Cool. So we have our for loop there. We're going to go average I is equal embedding. Yeah. Now we're going to do another for loop down here. We're going to go integer I equals 0. If I can type. And then the I is going to be greater than dimension. Then we're going to increase it each time. Plus plus. It's going to walk through our iteration. I less the, or is dividing equal length. Cool. So let me just double check. We got everything here. We got our length, we got our dimension, created our average. We walk through our embedding, creating the average there, and then creating the average. Bam, okay, that's good. So the last thing we need to do is our cosine similarity. That's up here. It's going to take the cosines, and that's how we're going to compare the dimension of where they are, the vector space, I should say. So essentially that's, if we were to take a word and break it apart, or take a sentence, break it apart, and try and say, hey, these words are similar, I like to think about it like candy. So if we had a red M&M and a green M&M, and then we had a yellow M&M and a blue M&M, and then somewhere in between those shades, we'd be able to say that they're somewhat related, right? If a light red M&M would be close to a red M&M, so that's going to give you direction, right? Now, what if instead of a pink M&M, you had a pink Skittle? That's still going to be similar, but it's going to be a different candy, so that would be in a different direction. Maybe those are above the M&Ms, so that's your direction and your distance, and that's going to give you, the mathematical representation of the similarity there. Again, trying to explain it, but I'm not a mathematician. So plenty of things you can Google to explain that, or feel free to message me. So now we're going to bring our private static double, and we're going to do our cosine similarity and pass through that our float vector A and our float. That's going to be our vector B. So those are our two vectors comparing, right? Now we're going to create a double. We'll call it dot product equals 0, 0, assigning it to nothing. Double norm A is going to also be equal to 0, 0. And then we're going to do double norm B equal to 0, 0. And then we're going to walk it through the loop again, make sure I equals 0. I is going to be less than the vector A dot length, and I is going to increase through each iteration. So the dot product is going to be plus equal. Then we're going to do some math here, so we're going to use math dot pow vector A, and then 2. Then we're going to do norm B, or norm A, sorry. It's going to be plus equal math. Oops, I did something wrong here. This is actually supposed to be down here. My apologies. So dot product's actually going to be plus equal vector A times vector B. There we go. Okay, and then norm A is going to be plus equal math pow. And then norm B, as you may have guessed, is going to be similar. Math pow. E I also, and this is going to return our dot product divided by our math square root of norm A times the math square root of norm B. I spelled something wrong. There you go. Cool. So if we did this right, it's going to compare these two sentences, and it should pop out a number for us. There we go. 61. So it's saying that it's about 61%. So let's try this again. Let's say the happy dog. Sad dog. That again. %82% say that they're pretty similar. Other than that, now if we did this right, when we say that they're both happy dog, it should give us a near one as being completely similar. The lower number less similar. Let's run that again. There we go. So you can see now it's using these models, which obviously have some error built into them. It all depends on the model that you use, but this is an example of a sentence transformer in Onnx format through Java, doing cosine similarity between two strings. I'll try and do a write-up for you, but hopefully this is helpful, and feel free to reach out if you need anything.